Okay, hello again. So in this session, we are going to derive the continuity and momentum conservation equation in integral form. So the title of this section is Continuity Equation in Integral Form. So we can write the continuity equation for a fixed general CV. So say you have a fixed general CV like here. And you want to write the continuity equation for this. So what we can write is rate of mass increase inside the CV plus net mass flux out of CV should be 0. Okay. So this is kind of the continuity equation or mass conservation equation that we want to write. So this means at the rate of the mass increase that is changing inside this CV, inside this control volume, how much the mass of fluid is changing in time should equal to the mass flux that is going out of this net mass flux that is going out of this CV. Okay. So for example, if the mass is increasing, the mass increasing inside the CV, that means that the mass flux should be coming into the CV based on this equation. Okay, so there should be a balance between the mass that goes out of that and the rate of mass increase inside the CV. Okay, so this is the continuity equation. And now we want to write this in terms of mathematical operations. Okay, so what I'm going to do is first for this one, for this term, I'm going to choose write the equations. So let's get started on that. So first we want to write it in terms of change of the mass only for one small element. So say we have an element here inside the control volume. It has a volume of dV. Okay, so we want to see what is the rate of mass. First of all, we want to see what is mass of that, and then calculate the rate of mass. So mass of dV is gonna be what? It is density times its volume, so rho times dV. And then we can, based on this, we can define the total mass of, so let me bring this a little bit higher. Okay. So I want to write something here. So the total mass of CV is gonna be what? Is gonna be the mass of all these small elements, or the sum of all these, the mass of all these small elements, which I can write it as an integral. So it's gonna be integral over the CV of rho dV. So this could be over the CV. And now rate of mass change inside the control volume, what do you need to do? So let me write it a little bit higher here. The mass of CV is gonna be rho dV let me just so the rate of mass change is gonna be, we just need to take the derivative with respect to time of the total mass inside this control volume, right? So this is gonna be rate of mass change. And then net mass flux out of CV. So we learned about mass flux before. What is mass flux? We have it here. This is mass flux, okay? So this is just n dot rho v times dA, okay? And we want to, this is just a mass flux that is going across small element of dA, right? So let's say we have it here. Let's say we have dV. I can plot it here. It's just one element, surface element of this control volume. And then this has a normal vector n. And in order to find, so the mass flux out of this CV just for one element is n dot, from here I can just write it down, n dot rho v, so you have it here, rho v times dA, so it's gonna be n dot rho v velocity times dA. And in order to get this for the whole control volume, you need to integrate it over the whole surface of the control volume, which is going to be around here, right? The whole surface of this arbitrary control volume. So it's going to be the integral. We need to take an integral over the CV, over the CS, the surface area of that control volume. So it's going to be sum over the entire CV surface. Okay. So now let's rearrange the terms in order to write the continuity equation. So continuity equation in integral form. Is as follows. Is gonna be partial over partial t of the integral of density rho times dV over the control volume plus the integral of n dot rho v, this is velocity times dA, equals to 0. Okay. So this is an important equation that you need to know, and this is the continuity equation in integral form. Okay. So I just want to say that you can also get this formula. So we just derived it based on this kind of principle that we defined here. But you can also drive this based on, if you have learned, especially if you might have heard it in your undergrad fluid mechanics course or in other courses. You can easily also drive this from Reynolds transport theorem. So I just want to talk about it a little bit here. So Reynolds transport theorem, you can also drive this formula. So let's see what it is. So Reynolds transport theorem is a general theorem about any system and control volumes, and it has a proof that I'm not going to go through that, but basically it states that the total or the material derivative of any quantity of the system, B system, with respect to time equals to partial t of the integral of rho b dv. So let me before that define what is B. So B system is defined as mass times small b, and B system is called an extensive parameter. Small b is called intensive parameter. Okay, so this is just a definition how we defined B system. So the Reynolds transport theorem states that dB system over dt, which is the material derivative of B system, equals to partial over partial t of rho small b times dV plus the integral over the surface of that control surface, the surface of that control volume of rho m dot rho v b dA. Okay. So for this, if you write this, you can derive both continuity and momentum equation. So for continuity, what you need to do is just set this small b here to 1. So I'm just going to set it to 1. So if you set b small b equals to 1, what you are going to get is dm over dt. This is the material derivative of mass with respect to time. It's going to be partial over partial t of rho. B is 1, so I just have it dv plus the integral of n dot rho v, and b again is 1, dA equals to 0. This is actually what I got here. If you look at it, it's the same. So this states that we can just get the material, we can just have the continuity equation by having this general theorem, which is Reynolds transport theorem. Okay. So let me also show it here. And this is very important theorem because you can derive continuity momentum equation from these two. But for momentum equation, I'm gonna use it from like this, but for momentum equation, instead of setting small b to 1, what you need to do is to set b equals to velocity. And if you set b equals to velocity, you are going to get momentum equation. Okay. So for momentum, B equals to V. Okay, so I'm going to derive it another way, and then you can check it yourself with using this Reynolds transport theorem. So I'm going to derive a momentum equation using, again, another from the first principles, but you can derive it using this Reynolds transport theorem as well. So the next topic is momentum equation in integral form. Integral form So I'm going to drive it by using the Newton's second law of motion. So Newton's second law of motion. So what we are going to say is rate of change rate of change of momentum inside CV okay, plus net momentum flux out of CV equals to resultant force acting on fluid in CV. Okay. So what is rate of change of momentum inside CV? Similar to this one, so this term was rate of mass change inside the CV. So instead of, we can just write, instead of mass, we just put momentum. So to add momentum, we just need to multiply this by velocity. So similarly, I'm going to get partial over partial t of the integral of rho times v. So I just need to multiply by velocity of dv. And then here I have the net momentum flux out of CV. So we have the net mass flux. What is mass flux and momentum flux? So this was mass flux, and here we have momentum flux. You just need to multiply it by a velocity. So this is the mass flux out of the CV, the net mass flux out of the CV. So in order to get the net momentum flux, I just multiply it by a v, velocity. So it's going to be n dot rho v times v dA, this we have plus, equals to the resultant force acting on fluid in CV, which is I just write it as sigma F. So this is just Newton's second law of motion, because what are these? These are just dA mv over dt, which is the material derivative of momentum with respect to time, which is going to be just ma equals to sigma f. This is what probably you have heard and you have you might remember, okay? And you can get this formula again by setting b equals to v here in this formula, and you will get the same formula that is given here, okay? So let's first see what is sigma f. So what are the forces that act on a fluid? So sigma f is gonna be composed of f of pressure. So the first one is the pressure changes, which are acting on the fluid. The weight of the fluid, so weight force. Viscosity is another force that we can have, and then plus external forces that are exerted on the fluid, for example, by channel or other things. So now I want to find what is the resultant force due to pressure differences acting on the fluid. So say you have again that arbitrary control volume, and there are many pressure forces that act on this control volume. So pressure could be high here, lower here, and different directions, right? With different magnitudes. So we want to see what is the net pressure force. So in order to calculate the net pressure force, so for each component, for each pressure, I have this n, the normal vector. I can calculate this normal vector. That is not necessarily in the same direction as the pressure. So what I'm going to do is I just get, as you see, the pressure force, the magnitude of that is inside, which is against our convention. So the net force that it acts is minus n dot p for just one element, right? So for just one element like this one, the net force, the net pressure is this, and in order to get this, for example, say for this dA, in order to get the net force, the net pressure force, you need to multiply it by dA. Okay, and in order to get the resultant force due to all these pressure differences that occur acting on this control volume, you need to take the integral over the surface of this control volume. So it's gonna be, we need to sum all these small forces. So this is gonna be the integral over the surface of these small elements. This is gonna give me just a sigma f here. So say here we have, for this one, we are going to get a df, and then you want to get the sum of all these df delta p. of all these to get the total resultant force due to pressure changes. Okay. The next force that I want to calculate is resultant force due to gravity, which is weight of the fluid, acting on the fluid. The second component. So for this, we just need to calculate the total mass and multiply it by g, gravitational velocity, acceleration, sorry. So here, say we have small element which has a volume dv, and in order to get the calculate the force, the gravity force on this, if a weight is gonna be rho, the density times volume, which is gonna be mass times g. Right? So this is mass times g. Is gonna give me the weight of that. Okay. So you can similarly calculate it for here, for all these small elements. And then you just need to sum it over the whole control volume. So this is over control surface, this is over control volume of rho g dv So now you get the integral to get the sum over the whole control volume. And so rho dv is mass of one element of the fluid and weight is just mg. So now we have found two resultant force. And now I want to write the whole the whole momentum equation in terms of in integral form using these two forces that we define. So it's just going to be as follows. So first we have this term, which is rate of change of momentum inside CV. I'm just going to copy it here. Paste. Then we have the second term, which is what? Which is this term, which is the net momentum flux out of CV. So let me just remove that part. Okay. And then this equals to the sum of the forces. So what are the forces? The first force is this pressure force. So I'm just going to write it minus integral N PdA plus the second one is the weight of the fluid. So it's going to be rho g dv, and then we have other terms like viscosity plus external forces. So this is going to be the momentum equation in integral form. Okay, so let me wrap up what we learned today. And in the next lecture, I'm going to solve one example for using continuity and momentum equation in integral form and find, for example, one of the forces, external force, and then another example to find drag force exerted on the plate by the fluid. Okay, so let me quickly wrap up what we learned today. So today we started with mass conservation in integral form using the large CV. So we define this large CV, and then for a steady flow, we got this conservation of mass. And then we define the concept of flux, which is the amount of something being transported across a surface per unit time. And then using this dot product definition for two vectors and these conventions that we have, we define this volume flux. This is volume flux n dot v times dA. Then we have mass flux, momentum flux, and kinetic energy flux. We can have heat flux, and anything else is just defined as this. Okay, and then we derive the continuity equation in integral form. So for a fixed general CV, we wrote this principle for the mass conservation, and then so we found this mass conservation in terms of integral form. And then I just talked about Reynolds transport theorem, which is a general theorem that can be applied to control volumes. And so this is how it is defined. So and you can just get different equations like continuity by setting small b equals to 1 and small b equals to v. You're going to get momentum equation. So I used Newton's second law of motion to derive the momentum equation. So we just wrote the Newton's second law, and then for a control volume, and we found equals to the sigma of the resultant forces. So we wrote the important forces that act on a fluid control volume. So the first one is the pressure changes. So this is going to be the pressure change in integral form. And also this is going to be the weight of the fluid. And so we found this general formula which is the momentum equation in integral form for fluids. So again, in the next lecture, I'm going to solve some examples of this, and after that, we are going to drive the continuity and momentum equation in differential form using Gauss's or divergence theorem. Thank you very much, everyone.